So today we're going to begin a new unit working with roots and radical expressions, or radical functions rather. And today we're going to look at how do we work with roots and radical expressions and simplify them. Right? So that's really our one objective for today. How do we simplify? And I'm going to use this term nth roots, which means it could be any root that we're taking: square root, cube root, fourth root, fifth root, etc. So let's begin by defining some terms we're going to be using here. Here's a radical expression, right? A equals the nth root of B. So let's label some of the parts of this. The symbol itself, we call that the radical sign. The number inside the radical sign, we call the radicand. The root that we're taking, the n value, we refer to as the index. And A, what we're trying to find, is the root. Okay? Now, this is written in radical form. We could also, well, let me back up. If we use words to describe this, we'd say A is the nth root of B. Now, if we wrote this in what I would call exponential form, it's really equivalent. Right, we're saying A raised to the nth power gives us B, okay? So these are two ways of writing the same relationships between A, the root, N, the index, and B, the radicand. So we would describe this with words as A to the n power equals B. All right, let's look at some examples. So since 2 squared equals 4, right, we would say 2 is equal to the square root of 4. It applies to other roots that we might be looking at. So 2 to the third equals 8, or we could rewrite this as 2 equals the cube root of 8. And we can go on and on, right? 2 to the fourth equals 16, or 2 is equal to the fourth root of 16. Let's do one more. So 2 to the fifth is equal to 32, right? So that would be 2 times 2 times 2 times 2 times 2, 5 times gives us 32, or the way we would write that in radical form would be 2 is the fifth root of 32. All right, so what are the other possible roots? Now, what do I mean by possible? So commonly, we just state the positive root, but in some cases, we can have negative roots. So let's look at what those cases would be. So 2 equals the square root of 4. Yes, that's true. But does negative 2 also give us the square root of 4? Yes, it does, right? Because we could either say 2 times 2 is 4, or negative 2 times negative 2 gives us 4. How about negative 2 being the cube root of 8? Well, if you think about that, negative 2 to the third power, right, would give us negative 2 times negative 2 is positive 4, but then times another negative 2 would give us negative 8, and we need a positive 8. So that doesn't work. If we take the cube root of 8, we would not get a negative 2. How about the fourth root of 16? Can we get a negative 2? The answer is yes, right? Because negative 2 times itself 4 times would give us a positive 16. And let's look at a couple more. So can we get the fifth root of 32 give us a negative 2? So this is similar to the cube root up here, right? If we're raising negative 2 to an odd power, then we're always going to wind up with a negative, and we're looking for a positive here. So that doesn't work. Let's look at one more. Can we get the sixth root of 64 to be negative? Well, yes, right? If we multiply negative 2 times itself 6 times, an even number, then we'll get a positive 64. All right, so can we put a rule together? Yes, let's do that. If you take the even root of a positive number, then we're always going to have 2 real roots, one positive and one negative, okay? If we take the odd root of a positive number, then there is only going to be one positive root, okay? So those are the cases here where we took the cube root and the fifth root, we only get a positive 2 or positive root. All right, let's look at some other cases here. What happens if we take the square root of a negative number? So we can't do that, right? At least we won't get a real root of a negative radicand. If you think back to when you studied quadratic functions, we introduced the concept of an imaginary number. So that's where we can come up with an expression for the square root of a negative number using I, the imaginary number or symbol that equates to the square root of -1. But in this unit, we're only going to be working with real roots. So in this case, we'd say, no, we cannot find a real root of a negative radicand as long as we're taking the square root. How about cube root? Well, yes, right, -2, because if we multiply -2 by itself 3 times, we would get -8. So that works. How about the fourth root of -16? Well, that's going to be similar to the first one, right? That will not give us a real root, only an imaginary. How about fifth root of -32? Well, -2 would work, right? -2 times itself 5 times will give us a -32. All right, so you can see the pattern here. So what's the rule for this? It says if you take the odd root of a negative number, then there is only one negative root. And if we take the even root of a negative number, then we get no real roots. All right, so we can kind of summarize that in a table, right? So if you haven't taken notes yet, this would be a great thing to put in your notes because it gives us the 4 cases that we just looked at. Okay, the number of real roots of a real number. So if the radicand is positive and the index is even, we get 2 real roots, 1 positive, 1 negative. If the index is odd and we have a positive radicand, we get 1 positive root. Okay? If the radicand is negative, no real roots, we get imaginary but not real. And if we have a negative radicand and the index is odd, so like cube root or fifth root, then yes, we do get 1 negative root. So here's some examples, right? Okay, let's apply this and just see if we can figure out how many real roots. We're not necessarily trying to find out what they are at this point, but just can we determine how many real roots we have? All right, let's try this. So fifth root of 32, which case is that? Well, it's a positive radicand and the index is odd. So that's going to give us 1 positive root. How about square root of -16? Well, that's the case where we'll have no real roots, only imaginary. How about cube root of -27? So that is the odd root or odd index of a negative radicand. So yes, we would get 1 negative root with that. And the last one, fourth root of 81, that's an even index of a positive radicand. So we would get 2 real roots, 1 positive and 1 negative. Now, we're going to be working with radical expressions, and the next step here in the lesson is how do we simplify them. And so it's good to have somewhere handy a list of some of the more common even and odd roots. Now, in class, right, we would have a paper, you'd fill this out, you refer to that. I'm going to post this as a separate PDF. If you want to take the time to put this in your notes, that's fine, but it's going to be useful to you to refer to this. So you may want to save this on your Chromebook, someplace where you can pull it up easily and refer to it when you're working on the assignments, and it will be helpful throughout this whole unit here. So notice how this works, right? We have square roots, cube roots, fourth roots, and fifth roots, and then we have them for the first 4 cases here, okay? So again, I will post this in the classroom as a separate document so you can pull it up for easy reference. All right, so let's do some practice here. We want to find all real roots. So square root of 144. Now your calculator also is handy for finding these if they don't show up on that table that I just shared. So square root of 144 is 12. Question is it a positive 12, negative 12, or both? Well, what case do we have, right? It's the even index 2 of a positive radicand. So that's going to give us both a positive 12 and a negative 12. Let's look at another one, cube root of 27. So we have the odd index of a positive radicand. The answer was 3, but it's only going to give us a positive 3. How about cube root of a negative 125? So we have an odd index, a negative radicand. So this is going to give us one negative root, and the root is 5. All right, let's try a few more, see if you can figure these out. So we get both a positive and negative 2. Fifth root of 32. We're going to get one positive root of 2. And fourth root of negative 81. So we'd get no real roots, right? We have an even index and a negative radicand, only imaginary. All right. So the next, well, really the rest of the lesson is looking at how do we simplify radical expressions, okay? So let's go through an example here. Cube root of 8. Now, since 8, we can rewrite that as 2 to the third power, right? Let's put 2 to the third in as the radicand. Now, here's the whole strategy around simplifying expressions. If we can have the index the same as the exponent of the radicand, then it simply will simplify to 2. Okay, the root is going to be equal to the base of the radicand. So think of it this way. Taking the cube root of a number and raising it to the third power are what we would call inverse operations, right? They're going to cancel each other out. And so all we're left with is the base of the radicand, the 2. So our goal here when we simplify is to rewrite what's inside the radicand so that it has exponents that match the index. So let's just look at a couple more examples, make sure we have this concept right. Cube root of 5 to the third would give us 5, right? Because the index and the exponent match. Fifth root of 4 to the fifth would give us 4, right? So it works with integers. Does it work with variables? Yes, it still does, right? So this would just give us x. Fifth root of y to the fifth gives us y. And square root of z to the second power gives us z, okay? So this is going to be a very helpful strategy here as we simplify expressions. So let's see how we would apply this and use it. So here's an example. We want to find the third root of x to the fifth, okay? Now remember, our goal is to rewrite x to the fifth with factors and have as many of those factors have the same exponent as our index, in other words, 3. So let's do that. We can take x to the fifth and write it as an x cubed, but then what else do we still need to include as a factor, right? We need another x squared. So remember, properties of exponents, if we're multiplying 2 powers, we're going to add the exponents. So the 3 and the 2 have to add up to the 5. Okay, so now we look and see where do we have the same exponent as the index. And if we have that, then we can bring the base out of the radical. If we don't have that, it stays inside the radical, right? So in this case, we have x to the third power, so we can bring out an x, but we're going to keep x squared inside the radical. So this may not look more simplified, but this is how we simplify a radical. So x times the cube root of x squared. Let's try another one very similar, right? We have cube root of x to the sixth. So we want to factor it using as many perfect cubes, x to the third, as we can. So how many x to the thirds do we have in x to the sixth? Well, we're going to have 2, right? An x cubed and an x cubed, which means we can bring both x's out of the radicand and we have nothing left inside, right? So our final answer is just going to be x squared. Let's do one more, cube root of x to the 8th. So again, we're going to factor it with as many perfect cubes. So we can have 2 x cubes, right? That would give us x to the 6th. So we're going to need 2 more to get back to the original x to the 8th. So we'd have an x squared there. All right, so we can bring out the 2 x's, but we're going to leave the x cubed inside the radical. So if we simplify this, right, we're going to have x squared times the cube root of x squared. All right, let's mix it up a little more. We're going to throw in a coefficient of 8 and have 2 different variables here, okay? But the approach is the same. We're going to first just take each factor and say, can we rewrite it as a perfect cube? So let's begin to do that. So can we rewrite 8 as a perfect cube? Well, yes, 8 is a perfect cube, right? That's 2 to the 3rd power. How about x to the 4th? Well, we can write that as x to the 3rd, but we need another x, right? Or x to the 1st. And then y to the 6th, we can factor that as a y cubed and another y cubed. Okay, so this is actually the hardest part here, right? Is rewriting it with factors that have x cubed plus whatever remaining factors we need. So now what can we bring out? Well, we can bring out the 2, we can bring out one of the x's, we can bring out both of the y's, and what's left inside? We really just have the x. So if we simplify that, we can multiply the 2 y's together, that'll give us y squared, and we still have cube root of x. The x is still remaining in the radicand. All right, let's try a couple more here, see if you can do these. Square root of 16x squared. All right, so 16 we can write as 4 squared times, and then x squared is already a perfect square. So we can bring out both the 4 and the x. Okay, so we just get 4x in this case. Let's try another one, see if you can do this. All right, x to the 4th, y to the 6th. We can factor that as 2x squares and 3 y squares. Now, why are we doing square? Well, we're taking the square root. Now remember, square root, we don't necessarily have to put 2 as the index. You can put it in there, there's no problem with that. But if it has no index, that just means that the index is 2. All right, so how many x's can we bring out? We can bring out 2 x's and 3 y's. Right? So basically everything will simplify. We won't have anything left inside the radical. But let's go ahead and multiply these together. So we wind up with x squared times y to the 3rd power. All right, let's try another one. Cube root of 27y to the 6th. So cube root now, right? So we want to rewrite this as perfect cubes. So 3 to the 3rd gives us 27. Y to the 6th, we can factor into a y cubed and another y cubed. So we get 3 and y, they can all be brought out of the radical, nothing left inside. So our final answer is 3y squared. All right, that's it for this lesson. The assignment will give you some practice identifying what type of roots we have for different situations, and then several problems where you get some practice at simplifying radical expressions. Okay, thanks.